Begin with a sound almost no one remembers hearing, a newborn swallowing. In the first hours after birth, the human mother produces colostrum, a thick golden fluid dense with antibodies, followed within days by mature milk. This liquid is not simple. It carries fat, protein, minerals, and one particular sugar that defines the entire story ahead. That sugar is lactose, and it exists nowhere in nature except in the milk of mammals: cow, goat, camel, whale, human. All of them fold this sugar into the fluid meant for their young. Lactose accounts for roughly 7% of human milk, more than in the milk of almost any other species. It fuels the explosive growth of an infant brain, feeding neurons and building the fatty sheaths that wrap developing nerves. Milk, at its origin, is a private chemistry. It is a signal sent from one body to another, a bond written in molecules and timed to the earliest days of life. A mother's body reads the infant's needs and adjusts the recipe, thinning in summer heat, thickening for a hungry night. Everything about it says temporary. This is food for beginnings, not for a lifetime. And here lies the quiet paradox at the heart of our documentary. Lactose, this gift built for infancy, cannot simply be absorbed. It is a large molecule, a double sugar, too big to cross the wall of the gut intact. Before the body can use it, lactose must be split apart into simpler sugars the bloodstream can carry. That splitting requires a specific tool, a molecular blade tuned to one job. Without it, lactose passes through the small intestine untouched, drifting onward to where bacteria wait. In the newborn, that tool is present, abundant, ready. The system works flawlessly for the child at the breast, but nature designed this arrangement with an expiration date, a schedule that assumes milk will vanish from the diet once childhood ends. No adult body, for millions of years, was built to drink it. To understand why, we must meet the enzyme that makes milk digestible and learn the moment it is designed to disappear. The tool has a name, lactase. It is an enzyme, a protein that lines the surface of the small intestine, anchored to tiny finger-like folds called villi. Its single purpose is to grab each molecule of lactose and cleave it into two smaller sugars, glucose and galactose, which the gut absorbs with ease. In a nursing infant, lactase works constantly, present in enormous quantity along meters of intestinal wall. As long as it is there, milk is nourishment. But lactase is governed by a gene, and that gene follows a timetable. In most mammals, and in most humans across history, the gene dials down after weaning. Production falls sharply, often by 90%, sometime between the ages of 2 and 5. By adulthood, the enzyme has nearly vanished. This is not a defect. It is the original, ancestral design, the default setting for our entire lineage. Evolution saw no reason to keep building a tool for a food that would never appear again. When milk stops, the machinery powers down. Consider what this off switch meant. An adult without lactase who drinks milk sends undigested lactose deep into the colon. There, gut bacteria seize it and ferment it, releasing hydrogen, carbon dioxide, and methane. The result is bloating, cramps, and worse, the familiar misery we now call lactose intolerance. For our ancestors, this was not a disorder. It was simply the human condition. Draw a map of the world's mammals and the pattern holds everywhere. Cats, dogs, horses, elephants, whales, none drink milk as adults, and none can. The chimpanzee, our closest relative, loses lactase after infancy just as we do. This shared trait reaches back tens of millions of years, older than our species, older than our genus. It is written into the deep architecture of who we are. So the situation, some 10,000 years ago, was clear and unpromising. Any adult human who found a pail of fresh milk faced hours of digestive punishment for drinking it. The biology was locked. And yet, at exactly this moment, in a handful of villages in the Near East, humans made a decision that made no sense. They began keeping animals for their milk. The place was the Fertile Crescent, an arc of well-watered land curving from the Levant through Anatolia toward the Zagros Mountains. The time was roughly 10,000 years ago in the early Neolithic. Here, humans had already begun planting wheat and barley, settling into permanent villages of mud brick and stone. Now they took a further step. They captured, penned, and bred wild animals, first sheep and goats, then cattle descended from the massive wild aurochs and pigs. The domestication of livestock reshaped human life. Herds provided meat, hides, bone, and manure to fertilize fields. Animals could be driven, counted, inherited, and traded. A living herd was wealth on the hoof, a store of food that walked itself to water. At sites like Catalhoyuk in central Anatolia, archaeologists find dense layers of animal bone, evidence of communities built around their flocks. But the bones reveal something stranger. When researchers examine the age and sex of slaughtered animals, they find patterns that hint at more than meat. In some herds, males were killed young while females were kept alive for years, long past their prime as sources of flesh. A female kept living is a female kept for what she produces continuously, offspring, and milk. This is the puzzle at the center of the chapter. These first herders were, biologically, the same lactose-intolerant humans we have described. Their adult guts had switched off lactase in childhood. Drinking fresh milk should have brought them cramps and distress. And yet the herd management, the careful sparing of females, points toward dairying at the very dawn of animal keeping. Why milk animals you cannot digest? Why arrange an entire economy around a liquid that punishes the adults who drink it? The bones alone cannot answer. They tell us which animals lived and died, but not what flowed into the pots and stomachs of the people who kept them. For that, we need harder evidence. A chemical fingerprint left behind by milk itself, sealed and forgotten for thousands of years. That evidence exists. It is trapped in the clay of the pottery these farmers made and broke and buried beneath their floors. Fired clay is porous. When ancient cooks heated milk in an unglazed pot, microscopic fats seeped into the vessel walls and lodged there, shielded from air and decay. Thousands of years later, chemists can extract those fats and read them. The technique is called lipid residue analysis, and it has rewritten the story of dairying. Researchers grind a few grams of a potsherd, dissolve out the trapped lipids, and feed them into a gas chromatograph and mass spectrometer. The machines separate the molecules and weigh them one by one. Milk fats carry a distinctive signature, specific fatty acids, and a telling ratio of carbon isotopes that distinguishes dairy fat from the fat of carcasses. When the reading shows this signature, the verdict is clear. Milk was in this pot. The results have been startling. At Neolithic sites across Anatolia, potsherds nearly 500 years old carry unmistakable dairy residues. In the marshy lands of what is now northwestern Turkey, some of the earliest evidence pushes the practice back further still. From there, the signal follows the spread of farming across Europe, appearing in the Balkans, in Central Europe, and reaching the British Isles and the Baltic within a few thousand years. Dairying traveled with the farmers, a technology carried westward pot by pot, herd by herd. And here the puzzle sharpens into a paradox. These pots prove that people were processing milk on a large scale, generation after generation, for thousands of years. Yet the genetic evidence, drawn from ancient DNA, shows that the mutation allowing adults to digest lactose was still absent or vanishingly rare across all this time. The farmers making milk fats in their pottery could not, by and large, digest fresh milk as adults. Culture had run far ahead of biology. Dairying was not waiting for humans to evolve. It was flourishing among people whose bodies were still switching lactase off in childhood, just as their ancestors had. The practice spread across a continent before the gene to support it existed in any number, which forces a question the residues cannot dodge. If they could not drink the milk, What were they doing with it? The answer lay in transformation. The answer was to change the milk before drinking it, to attack the troublesome lactose outside the body rather than inside it. And the tools for that already lived in the milk and the air. Bacteria leave raw milk in a warm vessel, and wild microbes colonize it. They feed on lactose, consuming the very sugar that human adults could not, and convert it into lactic acid. The milk sours, thickens, and curdles. In doing so, its lactose content plummets. What was once indigestible becomes tolerable. This is fermentation, and it was humanity's first workaround. Yogurt and soured milk represent the simplest form. Bacteria do the digesting in advance, so the gut has less lactose to face. But farmers pushed further. By separating the solid curds from the watery whey, they concentrated the milk into cheese. Crucially, most of the lactose drains away with the whey, the liquid poured off in the making. Aged and ripened cheeses can lose nearly all their lactose, becoming safe even for adults with no lactase at all. The archaeology confirms this ingenuity. In Poland, sherds of pottery, roughly 7,000 years old, are pierced with small holes, the same pattern seen in later cheese strainers used to drain curds. Lipid analysis of these strainers found milk fats concentrated in exactly the way cheese making would produce. Here was direct evidence. Neolithic Europeans were separating curds from whey, manufacturing an early cheese, turning a hostile food into a storable, portable, digestible one. Cheese and fermented milk offered more than comfort. They preserved the nutrition of a herd through seasons of scarcity. A wheel of cheese kept for months what fresh milk lost in a day. It carried fat, protein, and calcium in a form that traveled and stored. Culture, in other words, had solved the milk problem entirely, without changing a single gene. For thousands of years, this was enough. Fermentation let lactose-intolerant people build economies on animals they could not otherwise fully use. The biology stayed locked, and it did not seem to matter, which makes what happened next so remarkable. Somewhere on the edges of this world, in a single human body, the ancient off switch broke, and the enzyme never shut down. The workaround was clever, but somewhere along the way the body itself began to change. On chromosome 2, upstream of the lactase gene, a single letter of DNA flipped. In Europeans, the culprit is a variant called -13,910 C to T, a lone base swap in a stretch of regulatory code. That tiny edit keeps a molecular switch jammed open, so the lactase enzyme never shuts down at weaning. A person carrying it drinks fresh milk at 40 as easily as at 4. One mutation, one letter, an entire adult diet unlocked. But where did it begin? For years, scientists assumed the change arose among early Anatolian farmers who first carried cattle into Europe. The DNA told a stranger story. When researchers sequenced hundreds of ancient skeletons, the -13,910 T variant was almost absent in Neolithic bones. Even 5,000 years ago, when pottery already dripped with milk fat, the gene for lifelong digestion was vanishingly rare. Then, around 3000 BC, a new people surged westward, the Yamnaya, herders of the Pontic-Caspian steppe, driving wagons and cattle across the grasslands north of the Black Sea. They swept into Central Europe during the Bronze Age, remaking languages, burial rites, and bloodlines. Buried within their genomes, at low frequency, rode the lactase persistence allele. It was not yet common even among them, perhaps a few percent, but it was moving. From that steppe reservoir, the variant spread, generation after generation, its carriers leaving more descendants than their neighbors. By Roman times, it was climbing. By the Middle Ages, it dominated Northern Europe. Today, more than 90% of Danes and Swedes carry it, while in southern Italy, the figure drops toward 40. The gradient still traces those ancient migrations across the map. Here is the puzzle that keeps geneticists awake. This single mutation was selected harder and faster than almost any other in the human genome, sweeping through populations in only a few thousand years. Evolution rarely moves at such speed. Something was pushing, relentlessly, favoring anyone who could drink milk unspoiled. But cheese already existed. Fermentation already worked. So why did biology bend so violently to solve a problem culture had already answered? It is the sharpest question in the whole story. If cheese and yogurt had already stripped lactose to harmless levels thousands of years earlier, why did the lactase gene spread with such ferocious speed? Selection this strong implies life and death, not mere comfort. Scientists have proposed competing answers, and the debate is far from settled. The first is famine. When harvests failed, a herder who could drink whole fresh milk gained calories, fat, and protein that a lactose-intolerant neighbor could not stomach without cramps and diarrhea. In a starving season, that difference decided who survived to reproduce. A 2022 analysis of ancient genomes and thousands of pottery residues argued that lactase persistence rose fastest precisely when populations crashed during periods of famine and dense settlement. The second answer is disease. Crowded villages bred pathogens, and dysentery drains the body through fluid loss. A person with severe lactose intolerance who drinks milk to survive a shortage floods an already sick gut with more diarrhea. Under epidemic stress, the mutation that let milk pass cleanly could mean the difference between recovery and death. Then there is clean liquid itself. In an age of contaminated wells and stagnant ponds, milk from your own animals was a comparatively safe fluid, drawn fresh and drunk immediately. Hydration without infection was a quiet daily advantage. Finally, vitamin D and calcium. In the dim, sun-starved north, where skin makes little vitamin D, milk delivered calcium and, some argue, helped the body use it, guarding against rickets and brittle bones. This may explain why persistence climbed so steeply toward the cloudy Baltic. Famine, disease, safe water, sunlight, poor skeletons. The pressures likely worked together, varying by place and century. What is certain is the outcome. Natural selection seized on that single-step mutation and drove it through populations at breakneck pace, rewriting the digestive fate of entire nations. Yet Europe was never the only theater. Far to the south, on different continents, other peoples were herding other animals, facing their own scarcities. And their bodies, we now know, found their own separate roads to the very same gift. The European story is only one chapter of a book written many times over. Travel south into Africa and Arabia, among cattle herders and camel nomads, and you find people who digest milk into old age just as easily as any Dane. But when geneticists read their DNA, the letter that flipped was not minus 13,910T. It was something else entirely. In East Africa, among pastoralist groups like the Beja, the Nilotes, and the peoples of Kenya and Tanzania, researchers identified a cluster of different variants, minus 14,010 G to C, minus 13,915 T to G, minus 13,907 C to G. Each sits in the same regulatory stretch of the lactase gene. Each jams the same switch open, yet each arose separately from a different mutation in a different population. The minus 13,915 variant is common across the Arabian Peninsula, likely spread with the domestication of the camel and its rich milk. The minus 14,010 change swept through cattle herding communities of the African savanna, estimated to have risen within the last few thousand years, driven by the same kind of intense selection seen in Europe. This is convergent evolution written into the human genome. Milk applied the same pressure on separate continents, and biology answered independently, again and again, always targeting the same tiny patch of DNA but by different routes. At least 5 distinct lactase persistence variants are known worldwide, arising in Europe, Arabia, and multiple regions of Africa, each a separate roll of the genetic dice that happened to land on the same solution. The pattern is unmistakable. Wherever people committed to herds, wherever survival leaned on the udder of a cow, a goat, a camel, natural selection favored anyone who could keep drinking. The mutations differ. The outcome converges. It is one of the clearest proofs in all of human genetics that a food, a cultural choice, can shape our species, code across the entire planet. And so we return, finally, to the beginning, to a chemistry meant only for newborns, a sugar no adult was ever built to break down. How did that infant's gift end up rewriting the biology of billions? Gather the threads now, and the pattern of 10,000 years comes clear. It began with a bond meant only for the newborn. Mother's milk, lactose, and the enzyme lactase that switched off at weaning in nearly every mammal, our ancestors included. For most of human history, adult milk was a poison of cramps and sickness, a food our bodies were never built to drink. Then, around 8000 BC in the Near East, people began herding cattle, sheep, and goats. The pottery remembers it, milk fat trapped in clay across Anatolia and Europe for thousands of years before any adult could easily digest a fresh cup. Culture leapt ahead of biology. Fermentation and cheese-making stripped away the lactose, letting whole populations profit from their herds while their genes stayed unchanged. That could have been the end of the story. It was not. On the Bronze Age step, a single letter flipped, minus 13,910 T, and rode westward with the Yamnaya into a continent that would become the milk-drinking heart of the world. Under the whip of famine, disease, unsafe water, and sunless northern skies, natural selection drove that mutation through populations at extraordinary speed. And it happened not once but many times. In Africa and Arabia, among cattle and camel herders, different mutations arose independently and converged on the identical gift. 5 separate rewrites of the same gene, scattered across continents, all because people chose to keep animals and drink what they gave. This is the rarest kind of story science can tell. Not biology shaping culture, but culture shaping biology. A dietary habit, a herding tradition, a jar of fermenting milk reached into the human genome and altered the frequency of genes across entire nations. It is still unfolding today, in populations where the trait is only now spreading, in bodies still adapting to a food we invented for ourselves. We were never meant to drink it. And yet, over 10,000 years, this single white liquid did what few forces ever have. Culture rewrote our blood and bones.